Okay. Okay. Thanks for the organizers for inviting me to give a talk. And good morning, European friends, and I think good afternoon for the Asia friends. My topic is magnetic bimerons in new materials. I'm a professor in Chinese University of Hong Kong, Shenzhen. I think I also want to thank the first two speakers, Winston Cross and Professor Nagosa. I think I will save a lot of time to introduce skyrmions because you have heard their wonderful talks. So I will just skip this part. And I think I can also skip this part. Yes, good evening from Australia, from New Zealand, also New Zealand. Okay, I think I can also skip this part. And you know that we have found skyrmions in a lot of material systems, from insulator to semiconductor to metals. So I just do a summary of different material systems to host the skyrmions. This is a theory, simulation and modeling talk. So I will just stress some simulation and theory part. To characterize a skyrmion, we need three quantities. First, skyrmion number and vorticity and helicity. For skyrmion number, it's also called skyrmion charge or topological charge. You can see that we have three pictures. Q equals +1, or Q equals -1, or Q equals 0. For Q equals 0, it means topologically trivial structure, like a bubble. Okay. The vorticity and helicity is described by this equation. So you can see that we also have three pictures. The first one is a Nile type of skyrmion. And in this case, vorticity is 1, helicity is 0. Second figure is block type of skyrmion. And vorticity is 1, helicity is half pi. The third one is the anti-skyrmion. So the vorticity is -1, helicity is 0. So to use the three different quantities, we can group the different spin textures, such as Nile type, block type, skyrmion, anti-skyrmion, etc. In recent years, our group have proposed some skyrmionic device, some concepts. So we proposed the spin wave-driven memory device, spin wave-driven transistor-like device, and the neuromorphic device made of skyrmions, spin logic device, and the microwave device, and also racetrack type of memory, etc. In this review paper, you can find the details of different application perspective. So please try to cite this paper if possible, because this is a task given by the editor. They want to boost the impact factor. And you know, to use skyrmion for example, racetrack memory, we need to look at the motion behavior of the skyrmion driven by current. There is a problem. That is that when you drive a skyrmion by a current, in addition to the velocity parallel to the current, there is a transverse velocity, which will push the skyrmion to the sample edge of the boundary. As mentioned by Professor Nagosa, in some cases, the skyrmion can be destroyed by the sample boundary. So this is a rather detrimental effect. So the skyrmion Hall effect, we want to suppress or try to get rid of skyrmion Hall effect for skyrmion for the racetrack application, racetrack memory application. So actually, our group have studied this problem since 2015. So we studied different proposals to suppress skyrmion Hall effect. In summary, there are three solutions. First one is to consider antiferromagnetic skyrmion. So I think also Professor Tritiakov's group and our group, we simultaneously proposed that you use antiferromagnetic skyrmion to get rid of the Skyrmion-Hall effect to achieve the straight motion parallel with the current direction. And in 2016, our group proposed that we can fabricate this synthetic, the soft synthetic antiferromagnetic bilayer skyrmion. In this case, the top layer and the bottom layer, the Magnus force acting on the top layer and the bottom layer, they will cancel, so that the total effective Magnus force will be 0. Then the bilayer skyrmion, they are coupled, they are banded as one particle, and it will be driven into steady state straight motion without any transverse deflection. This proposal have been experimentally confirmed last year by Professor Winston Krauss and Albert Fert group, also by Professor Ono's group. So the third solution is about the skyrmionum. So we know that from the right picture here, you can see that skyrmionum is just a donut type of spin texture. Topologically, it's equivalent to the coalition or the combination of two skyrmions with opposite skyrmion charge. Okay. Yes, the separation of Skyrmion-Hall effect will allow it to move straightly, a straight line with the current. Otherwise, it will be touching the sample boundary and will be destroyed. Okay. So, motivated by the separation of Skyrmion-Hall effect for racetrack memory applications, we can consider different type of spin textures. So, as introduced by this excellent review paper on the archive, you can see that there are different type of excitations in different background, such as, for example, the ferromagnetic materials, antiferromagnetic materials, and we can also have one-dimensional spin texture, or two-dimensional spin texture, or three-dimensional spin texture, as mentioned by Professor Nagosa, like a skyrmion tube, also the Hopfen, different bobber or tube or string, etc. So we can consider some textures beyond the skyrmions. So this is today's topic. So my talk is about magnetic bimerons. So if you look at this picture here, there are 3 panels, 3 columns. The first column is a skyrmion in traditional conventional ferromagnet. Second column is about skyrmion, about bimerons. And the third column is about anti-skyrmion. If you look at the bimeron, that is the middle panel, middle column, you can see that it's just you rotate the d vector along the y-axis 90 degrees out of plane, right? So the anisotropy is also in plane. So compared to skyrmion, the anisotropy is PMA perpendicular. The anisotropy for bimerons is in plane. So you can see that from the consideration of symmetry, you can treat the bimeron as rotating the magnetization of skyrmions by 90 degrees around x-axis or y-axis. So that is bimeron in in-plane anisotropy materials. So we will discuss 3 topics that in our recent work. So the first one is bimerons in frustrated ferromagnet. Second one is the bimeron in antiferromagnetic material. The third topic is the ferromagnetic bimeron. So the first topic is about the bimeron in ferromagnetic material with frustrated exchange interaction. If you look at the Hamiltonian, you can see that in this formula, there is no dm term. There is no dm interaction. The skyrmion can be stabilized due to the computation of J1 with J2 and J3. So you see that the J1, J2, J3, they have opposite signs, different signs. For example, in this case, J1 is positive, J2 and J3 are negative. And in some materials, J2 and J3 can be quite large. So in the simulation, J2 and J3 can be 0.5 or 1/2 of this J1 in certain materials. So the main results of this paper is about the formation of bimerons in frustrated magnetic material with different helicity, different vorticity. They can coexist simultaneously in this. So look at this picture here. It's the profile Z. This is basically the cluster of bimeron states. And this is the picture of profile of MX. So you can see that we can have the bimerons with different vorticities. And also we can have bimerons with different helicities, like in frustrated ferromagnetic layer with this implant anisotropy. Okay. The current driven dynamics of bimerons in frustrated magnet are dramatically different with the conventional ferromagnetic skyrmion with perpendicular magnetic anisotropy. So you can see that there are two rows. In the first row is for relatively smaller current density, and the bottom row is for relatively large current density. And in this case, the easy axis is along x-axis, and the spin polarization direction is 90 degrees with the easy axis anisotropy. So it can be positive y and negative y. Okay. So you can see for smaller current, the bimerons will be driven by the current into a steady state linear motion, straight line motion. But for relatively larger current, the bimeron will be driven into a circular or elliptical rotational motion. So this is very different with traditional skyrmions in conventional ferromagnet. I want to point out that if the spin polarization is along x direction, that is positive x or negative x, in the same direction with the easy axis anisotropy, then the skyrmions, the bimerons will be driven into this circular, the rotational motion. And you can also drive these bimerons into motion by spin current with spin polarization along the z direction. You know that for skyrmions, you cannot move the skyrmions if the spin polarization is along z direction, because you cannot break the symmetry, right? But this is different with the frustrated ferromagnetic skyrmion, bimerons. And the advantage of the frustrated bimeron or skyrmions is that we can use the helicity degree of freedom for information as an information carrier in racetrack memory. So as proposed in this work, they use anti-skyrmion to represent bit 0, skyrmion to represent bit 1. And they can design this racetrack memory. So in a similar way, we can use skyrmions or bimerons with different vorticity or different helicities to represent 0 and 1. So we can design a racetrack memory. In conventional ferromagnetic skyrmion, people use the existence or presence of skyrmion at bit 1 absence of skyrmion at 0, then you have problems because you cannot distinguish 0 state and the background, FM state. Also, you cannot control the interaction between skyrmions. You cannot control the spacing. But if you exploit the helicity degree of freedom to represent the different bits, you will solve the problem. The second topic is about the antiferromagnetic bimerons. So this work, you can see that we can study the staggered magnetization or Nile vector and the total magnetization. And we can also, derive this LLG type of equation for the Nile vector and the total magnetization. So similarly as the skyrmion, we can use the damping-like spin transfer torque or spin orbit torque to nucleate antiferromagnetic bimeron. And to give you a simple picture here, you know that we can compare AFM skyrmion and the AFM bimeron. The top column, the top row is about Nile vector. The bottom row is about this total magnetization, to give you some feeling about this AFM spin texture. And some important results is that the AFM bimeron can be driven by current, by the spin orbit torque, into very fast motion. So the speed can be a few kilometers per second. You know that in experiments, the AFM or ferromagnetic or antiferromagnetic domain walls can be driven into very large speed, like a few kilometers per second, due to the very small stray field. Okay, so the skyrmion or the bimeron can be made very smaller, so the array can be very denser, so that the stray field is minimized in this case, in AFM material. We also derived this analytical equation, which agree very well with the macromagnetics. And if we inject alternating current or AC current, we found out that the bimeron dynamics can be described by the modified Duffing equations. And the Duffing equations agree very well with the simulations. You know that we also found out a very novel phenomenon, that is chaotic motion or chaotic dynamics. So the chaos is characterized or described by the Lyapunov exponents. If the Lyapunov exponent is larger than 0, it means that the two neighboring orbits will separate. So very small difference in the initial condition will lead to very different results. So we just use these Lyapunov exponents to characterize the bimeron dynamics. It is found that in certain parameter space, the Lyapunov exponent is larger than 0, so that there are chaotic motion in the bimeron dynamics, especially for small damping factor alpha. Just recently, there is some experimental paper for AFM bimerons and AFM, merons and antimerons in the iron oxide capped with a platinum overlayer. So you can check out this archive paper. The last topic is about ferromagnetic bimeron. This work is a recent work. So from the Taylor equations here, you can see that the G vector or the Magnus force, as introduced by Professor Nagosa in his talk. For the ferromagnetic bimeron, the G vector, the coefficient is proportional, coefficient include this M1 divided by gamma 1 minus M2 over gamma 2. You know that M1 over gamma 1 is M over gamma, that is just the angular momentum, right? So gamma is the ratio of angular momentum with the magnetic moment. right? So this is just the angular momentum. If this m1 over gamma 1 minus m2 over gamma 2 is 0, it means that the angular momentum compensated for the two sublattices, and the g will be 0. It means there will be no Skyrmion-Hall effect, no Hall effect. So we performed some numerical calculations for spin polarization along x, along y, along z direction. Indeed, you can see that in the simulation, the gamma 1 and the over gamma 2 is fixed as 1.1. We change the ratio of ms1 over ms2 only when these two ratios they are equal. That is when ms1 over ms2 equals 1.1 equals gamma 1 over gamma 2. You can see that the transverse velocity will be 0. It means that that is the antiferromagnetic dynamics. So we numerically confirmed that at the angular momentum compensation point, the ferromagnetic bimeron dynamics just become AFM dynamics. So to conclude my talk, I have studied different textures in the materials with in-plane anisotropy. And I think ferromagnetic spin textures combines the advantages of ferromagnetic texture and antiferromagnetic textures. So the Magnus force is controllable, is weak, and the inertial mass is yes, and the speed can be relatively fast, like a kilometer per second. And because there is some finite net magnetization, so the detection becomes relatively easier compared to AFM. Finally, I want to acknowledge my group members, especially my postdoc and PhD, especially Xichao Zhang and Lai Chuanshen. Basically, this work done by the two PhD students. I also want to thank the international collaborators like Dr. Motohiko Izawa, Dr. Tretiakov, and Professor Guoping Zhao in these bimeron projects. And thanks for your attention.